The first speaker is Kansei Inamura, and the talk title is Fusion Surface Models. And please start the talk.
Thank you for the introduction. Today I'm going to talk about my recent work on 2+1 dimensional quantum lattice models. Today I'm going to talk about my recent work on 2+1 dimensional lattice models that are constructed from fusion 2 categories. And this work is based on a joint work with Kantaro Omori at the University of Tokyo. And he is a high energy physicist. And I'm doing condensed matter physics. And this talk is about condensed matter physics. And if you are interested in the details, you can find our paper on arXiv. So let me first give you a short summary of this talk. So the main message of this talk is that we can construct a large family of 2+1 dimensional quantum lattice models by using the data of fusion 2 categories. And we call these models fusion surface models. And in principle, we can define the fusion surface models on an arbitrary 2-dimensional lattice. But for simplicity, in this talk, I will only consider fusion surface models on a honeycomb lattice. And on a honeycomb lattice, each state in this model can be represented by a fusion diagram of this form. And also the Hamiltonian is defined by some manipulation on this fusion diagram. And I will elaborate on this point later in this talk. And the most important feature of this model is that the symmetry of this model is described by the fusion 2 category that we used as the input. So we can construct a lattice model from fusion 2 category, and this fusion 2 category describes the symmetry of the model. And this fusion 2 category symmetry is the most general finite symmetry in 2+1 dimensions, which includes any finite group symmetries, possibly with anomalies. And an interesting example of this fusion 2 category symmetry is the symmetry of anyons, which is described by a modular tensor category. And if this modular tensor category symmetry is spontaneously broken, then the model exhibits a topological order that is described by the same modular tensor category. And in particular, this includes chiral ones. So this suggests that the fusion surface models may provide natural candidates for chiral topological phases on the lattice. But for now, it is still unclear whether these models can indeed realize these phases or not. So this is the short summary of this talk. And the main topic of this talk is the fusion 2 category symmetry, which is a generalized symmetry in 2+1 dimensions. So let me begin with a brief introduction to this subject. So from a modern point of view, the symmetry of a physical system is defined by the algebraic structure of topological defects. So this means that if a physical system has some topological defects, then we say that this system has some symmetry. And the symmetry of this, the symmetry is described by this algebraic structure of these topological defects. So for example, if a physical system has an ordinary symmetry defined in a traditional way, then the corresponding topological defects are labeled by group elements, and they form group under the fusion of these defects. So that's why an ordinary symmetry is described by group. But here, the important point is that the topological defects of a physical system may not be group-like in general. And even in that case, we can think of the existence of these topological defects as the symmetry of the model. And the reason why we call this symmetry is that the symmetry defined in this way can do what an ordinary symmetry can do. So for example, if we have a topological defect, then we can define the symmetry action just by inserting the topological defect along the spatial direction, as shown in this left figure. And on the other hand, if we insert a topological defect along the time direction, then this defines a twisted boundary condition. So in this way, we can understand the twisted boundary condition and the symmetry action on the equal footing by using topological defects. So let us consider the conventional symmetry from this point of view. So for conventional symmetry, the corresponding topological defects are n-dimensional extended objects in an n+1 dimensional spacetime. This is because the symmetry operator acts on a whole space, which is an n-dimensional submanifold of an n+1 dimensional spacetime. So for example, in 1+1 dimensions, the symmetry defects are one-dimensional topological lines, and in 2+1 dimensions, symmetry defects are two-dimensional topological surfaces. So in other words, the topological defects of a conventional symmetry have codimension 1. So this is the first property. And another property is that these topological defects form a group under the fusion of these defects. So topological defects are labeled by group elements, and their fusion rules are group-like. And in particular, this group-like fusion rules implies that topological defects are invertible. So we find that conventional symmetry is associated with invertible topological defects of codimension 1. And so here we notice that the topological defects of a conventional symmetry have additional properties, namely they are codimension 1 and they are invertible. But these conditions are not necessary in the definition of the symmetry, because the symmetry is defined by the algebraic structure of general topological defects. So we can just drop these conditions, and dropping these conditions leads to the notion of generalized symmetries. So for generalized symmetry, the corresponding topological defects can have various codimensions. For example, we can think about one-dimensional topological lines in 2+1 dimensional spacetime, which have codimension 2. And the symmetry associated with such higher codimensional defects are called higher form symmetries. So this is one possible generalization of an ordinary symmetry. And another generalization is to relax the invertibility. So in general, topological defects can be non-invertible, and we can think about the symmetry generated by such non-invertible defects. And in particular, when the topological defects are non-invertible, then their fusion rules are non-group-like. So more specifically, the fusion of two topological defects, A and B, can be decomposed into the sum of topological defects. And here NABC is a non-negative integer that counts the number of topological defects C that appears in the fusion of A and B. And this non-negative integer is called a fusion coefficient. So there are two types of generalizations, namely one is the higher form symmetry and the other is the non-invertible symmetry. But we can also think about the mixtures of these higher form symmetries and non-invertible symmetries. And such a symmetry is generally described by higher category rather than group. Of course, this higher category includes an ordinary group symmetry. So for example, in 1+1 dimensions, the symmetry of a physical system is associated with topological lines and their topological junctions. And in particular, when the number of topological defects is finite, then it is known that such topological defects in 1+1 dimensions form a fusion 1 category, which is a very special example of a higher category. And of course, this fusion 1 category contains a finite group as a special case. So this means that finite generalized symmetry in 1+1 dimensions is generally described by fusion 1 category. And for this reason, finite symmetries in 1+1 dimensions are called fusion 1 category symmetry. So what is fusion 1 category? So basically, fusion 1 category is just a mathematical theory of topological lines in 1+1D. But more concretely, we can list the basic data of fusion 1 category like this. So the first datum is the set of topological lines, which are also called objects in the category theory. And the second datum is a set of topological junctions of topological lines, and they are called morphisms. And these topological junctions can be represented diagrammatically by using fusion diagram. For example, a trivariant junction of topological lines, 3 topological lines, A, B, C, can be represented by this kind of fusion diagram. And this trivariant junction is possible if and only if this topological defect C is contained in the fusion of topological defects A and B at the bottom. So in particular, this set of topological junctions contains the data of fusion rules. And the last datum is a set of complex numbers called F symbols. And they describe the crossing relations of topological lines as shown in this equation. And precisely speaking, these complex numbers must satisfy some consistency conditions known as the pentagon equation. But the pentagon equation is not super important in this talk, so I will not talk about it. So basically, these algebraic data define the fusion category, and this describes the symmetry in 1+1 dimensions. And we can generalize this structure to 1 higher dimensions. So in 2+1 dimensions, symmetry is associated with topological surfaces, topological lines, and their topological junctions. And when the number of topological defects is finite, then they form a fusion 2 category, which is a higher version or categorification of fusion 1 category. And for this reason, finite symmetries in 2+1 dimensions are called fusion 2 category symmetries. And the basic structure of a fusion 2 category is very similar to that of a fusion 1 category. So basically, fusion 2 category just consists of the set of topological surfaces, also called objects, and the set of topological interfaces of topological surfaces, also called 1 morphisms, and the set of topological junctions of topological interfaces, which are also called 2 morphisms, and the set of complex numbers that are called Kansei symbols. So, and just as in the case of fusion 1 category, 1 morphisms and 2 morphisms can be represented by fusion diagrams like this. So, and these algebraic data describe the symmetry in 2+1D. And the goal of this talk is to construct concrete 2+1 dimensional lattice models with this symmetry.
So is there a similar equation for like pentagon equation for tangent symbols?
Yes.
Should be, right?
Yes, there is a similar equation, but much more complicated. So we want to construct 2+1 dimensional lattice models with fusion 2 category symmetries. But as a warm-up, let me begin with 1+1 dimensions. So we want to construct 1+1 dimensional lattice models with general fusion 1 category symmetry. And to this end, we first choose a fusion 1 category C. That is going to be the symmetry of this model. And in addition to this, we also choose a single object, which we denote by rho. And we can choose this object arbitrarily. And from these input data, we can construct a large family of 1+1 dimensional lattice models with symmetry C. So let me first define the state space. The state space of this model is a vector space that is spanned by the fusion diagrams of this form. So each fusion diagram represents a state. And here, dynamical variables are objects on the horizontal edges and the morphisms on the trivariant vertices. And on the other hand, the objects on these vertical edges are chosen to the fixed object rho, which is not a dynamical variable of this model. So the dynamical variables are only on the horizontal edges and the trivariant vertices. And the configuration of these dynamical variables is constrained by the fusion rules. So this is the state space. And Hamiltonian acting on this state space is typically given by the sum of next nearest neighbor interactions. And here each interaction around the site I is given by the sum of this form. And here hi of f is some operator that is defined by this diagrammatic equation. And here, so what this operator does is to insert a topological line f between two adjacent vertical lines. And we can evaluate this diagram by using f symbols very explicitly like this. So, and here this coefficient w of f is an arbitrarily complex number as long as the Hamiltonian becomes Hermitian. And so this is a parameter of the model. So we have many parameters. And the sum is taken over all the simple objects of the fusion 1 category. So in this way, we can define the Hamiltonian of the model. And the 1+ dimensional lattice model defined in this way is known as the anion chain model. And an important feature of this anion chain model is that the symmetry of the model is described by the input fusion 1 category. And we want to generalize this construction to 1 higher dimensions. And so in order to construct 2+1 dimensional lattice models, we first choose a fusion 2 category C. And this will become the symmetry of the model. And then in addition to this, we also choose 3 objects, rho, sigma, lambda, and 2 one-morphisms F and G. And here, these 2 one-morphisms F and G are topological interfaces of topological surfaces, rho, sigma, and lambda. So these objects and one-morphisms are not independent of each other. But anyway, from this input data, we can construct a large family of 2+1 dimensional lattice models whose symmetry is described by this input fusion 2 category C. So again, we first define the state space. And in order to define the state space of the model, we first consider the vector space H that is spanned by the fusion diagrams of this form. So here, the dynamical variables are objects on each bracket, and also one morphisms on each edges, and also 2 morphisms on the vertices. On the other hand, the objects and one morphisms on these colored surfaces and their colored edges are the chosen objects, rho, sigma, lambda, and the chosen one morphisms F and G. And they are not dynamical variables of the model. So the dynamical variables are only on honeycomb lattice. So as you may notice, this vector space H is very similar to the state space of the anion chain model. This is a natural generalization of the state space of the anion chain model. But this vector space itself is not the state space of the 2+1 dimensional model. So the state space of the model is a specific subspace, which we denote by H0, of this larger vector space H. And this state space H0 is obtained by applying a projector that is given by the product of the so-called Levin-Wen stringnet operators on all the brackets. So the state space H0 is much smaller than the vector space spanned by all the fusion diagrams. But nevertheless, each state can be represented by a fusion diagram because H0 is just a subspace of H. And the Hamiltonian is given by the sum of local bracket operators denoted by HP, which acts only on single bracket. And this local Hamiltonian is given by the sum of this form. So again, this is very similar to the Hamiltonian of the anion chain model. And here the operator HP of F is defined by inserting a topological surface F below the bracket P. And the coefficient W of F is the parameter of the model. And so in this way, we can construct 2+1 dimensional lattice models, and we call these models the fusion surface models. And the most important feature of this model is that the symmetry of this model is described by the input fusion 2 category. And its action is defined by the fusion of topological surfaces or topological lines into the fusion diagrams from above. And this action automatically commutes with the Hamiltonian, basically because the symmetry action is defined from above, whereas the action of the Hamiltonian is defined from below. And so this means that our model has fusion 2-category symmetry. And for example, if the input fusion 2-category can be written as mod B, where B is a modular tensor category, then this describes the symmetry of the anyons in a topological phase. And spontaneously breaking the symmetry gives rise to a topological order B. And in particular, this includes chiral topological phases. So it would be very interesting to study the phase diagram of fusion surface models. So in summary, we constructed 2+1 dimensional lattice models that we call fusion surface models. And these fusion surface models have general finite symmetries that are described by fusion 2 categories. And it is natural to expect that these fusion surface models can provide candidates for chiral topological phases. But this is still an open problem, and further study is needed. So let me stop here. Thank you for your attention.
Any quick question?
So these models, are they gapped or gapless or both? Before symmetry breaking?
Before symmetry? In general, fusion surface model can be gapped or gapless.
Okay. But then you can do the symmetry breaking to get to gapped topological orders.
Yes.
Right. And I guess, can you do like a partial symmetry breaking so that you get a symmetry enriched topological order as well?
It's possible in principle.
Okay. Thanks.
Is there any string operator or such kind of construction that create excitations in this model?
I haven't analyzed the string operators for this model, but
okay, thank you.
Okay, time has come, so let's thank the speaker again.
Good afternoon. I'm honored to be here to give a talk about our recent work on the Hopf quantum double model and the weak Hopf quantum double model. But in this talk, I will just focus on the Hopf case. And this is a joint work with several of collaborators. The first one is Liang Cheng from the Chen Institute, and the second one is from the Dagmir, and the third one is Shen. And this talk is based on the several works. And we know that topological order is, there is several different definitions of the topological order. And now the generally accepted definition is for the gapped topological order is just the equivalence class of the gapped local Hamiltonians. And this equivalence class of gapped local Hamiltonians realize some kind of TQFT. And there are several physical properties of the topological order. Usually we can just detect the topological order with the topologically protected ground state space or the long range entanglement of this of the ground state of this topological order. And there is also other physical property like the topological entanglement entropy or the fractional statistics and so on. And this model is very interesting because now we have a question that what is the lattice model for a general case? And usually there are two major classes of these topological orders in the 2D. And the first one is the Levin model, and the second one is the quantum double model. And actually they are related to each other because we can just use a map. We can just map a quantum double model via some projection to the Levin model. And for the Levin model, if we equip the input fusion category with some extra structure, we can also map it to a quantum double model. So today my talk is focused on the Hopf case of the quantum double model. We know that the quantum double model is usually constructed from the finite group, and the Hopf case is more complicated, and it's a more comprehensive framework. So let me first remind some of the basic definition of the Hopf algebra. We know that a Hopf algebra there is two basic structures. The first structure is just an algebra structure, which means that we have a multiplication map and we have a unit map, and they satisfy some axioms. And there is another structure which is very useful, is the co-algebra structure. This co-algebra structure is a map that from the Hopf algebra to the tensor product of two Hopf algebras. This structure can be very useful in the many body quantum physics systems because we can just map a Hopf algebra to a multi-Hopf algebra tensor product. And they satisfy some properties, and there is another structure morphism called the antipode. This is also very crucial in the Hopf algebra case. And we will use a notation which is called Swedler notation, which means that very similar like the Einstein sum notation, which means that we can just denote the co-multiplication with this multiplication. We know that there may be some basis. We can expand this element into a basis, and they sum over them, that we can just omit the label subscript of this two element. So we get such a notation. And another notation is that we have a map, this is a map from the Hopf algebra to the complex number field. And this map can act all these Hopf algebra element, which means that we just act all the second element of this. And we can similarly do that F is on the right hand side and make a right action of this element. And now another important definition is just the quantum double. We know that the quantum double model, the name is just use this construction. The quantum double model is actually constructed from the Hopf algebra at its dual Hopf algebra. There are several constructions. We can choose for example, we choose the Hopf algebra, and the left side we choose the H-dual Hopf algebra. There is a co-op action, which means that the co-algebra structure is acted with a twist. We just the twist means that A tensor product B, we twist it as a B tensor product A, and this is one construction we use. Actually, we can use also the op case or other case or directly H-dual case to construct a quantum double. In this case, we know that the quantum double model, for the quantum double case, we know that the most crucial structure is just a multiplication structure. This is just can be written as this form. In this form, which means that we first take the co-multiplication of this element x, and we have three component. Then we act this with the third component with the antipode inverse. For our case, we just consider the C star Hopf algebra. So this is S inverse is just the same as S. And we have such structure. This is very crucial. We know that if we just consider these equations or these axioms, we know that we can consider x times y psi. This is a relation that we can see that this is just we take the second component of x and then do some such kind of relation. This is called a straightening relation. And using this relation, we can just find a model such that the model support a representation of this algebra structure. So this is the main aim of the construction. And we know before I start, let me first recall some basic definition of the quantum double model for the finite group. We know that for the finite group, if we just span it, if we just consider linear span of this finite group, we know that it's a Hopf algebra, and the multiplication is just if we just consider basis, it's just the group multiplication, and the unit is just the group unit. The co-multiplication is very special. It's just the two copy of the group element for the basis. And we can just take the linear span of this form. And for the co-unit, it just map every basis into the 1. This is just complex number 1. And the antipode is just take the inverse. And we know that for the KITP quantum double model, we just construct it as follows. We have a vertex operator and we have a face operator. For the vertex operator, we know we must consider the direction of each edge. If this is the start point of this edge, we will do the G inverse. If this is the terminal point, end point of this vertex, then we'll do it action on the left hand side. So we have two actions. The first action is the right group action, but we can take the antipode to make it a left action. And for the second one, it's a left action automatically. So in generally, we can just do such kind of left module action of the CG over the CG. And similarly, we can do a structure. This is actually also a left module structure, but this is from the CG's dual Hopf algebra to the CG. So this algebra structure is just regard the CG as the CG dual Hopf algebra, the CG dual left module. And in this case, if we define these two operators, we construct a model. If we just consider this is the black one as a lattice and the red one is the dual lattice, we can regard this as an operator, and we sum over all the vertex operator and the face operator, we construct a lattice model called the quantum double lattice model. The right one is just a chessboard representation. We can, if we just consider this and this, we will see that these are equivalent. There are many applications of this model in different fields. We know that for this, we can use this to do the quantum memory, and the most typical one is just the Tor code. And we can also do the topological quantum computation using the string operator or the ribbon operator in general. And there are also other applications of this model. And for our case, we want to generalize this to the, if we want to generalize this to the Hopf case, we'll face several difficulties. We know that it's not so straightforward to do this. So we need to find some approach to generalize this as, if we want to find some approach to generalize the finite group to the Hopf case, we know that we need to find a special element of the vertex and a special element of the face. The proper notion of these two concepts turned out to be the Hall integral of the Hopf algebra. Actually, the model is constructed in the following way. We know that we have the lattice. This is the black lattice. And for each edge, we just put a Hopf algebra on each edges. Then we take the product over all the edges. We get a total Hilbert space. And now, if we want to construct the vertex operator, we first introduce two left module structure, as I have mentioned. The first one is the canonical one, which means that this is just the multiplication of the H in H. This is the H action or the H. This is the canonical left module structure. And we can also construct a right module structure, which is induced by the right action, which is the H op action over the H from right hand side. And we can use the antipode to realize this and to make it into a left module. And in this way, we can just have a left module structure over H and a left module structure over H. And another way is just we consider H dual. We know that the H dual have a canonical Hopf algebra structure, and we can also do this. We just this is from H dual. By H dual, I mean that all the functions from the Hopf algebra to the complex numbers. And we can do this using the Swidler notation. We know that it acts on the second component of this element X, and we can do very similar things, and it can be proved that this is also a left module structure. So now we have two left module structure. The first one is H as a left H module structure. The second one is H as a left H dual module structure. It turns out that the face operator and face operator and a vertex operator can be constructed from two spatial elements. This is called Hopf integral. Hopf integral is a spatial element in the H, and it satisfies this condition, which means that if we multiply this L with X, we'll find that the X is cancelled in such a way. This is a co-unit of the Hopf algebra, so this is just a complex number. And there is another requirement that if this is called the left Hopf integral, and we can similarly define the right Hopf integral. If it satisfies this condition, when we call it a normalized Hopf integral, and if this element is normalized two-side integral, it's called a Hopf integral. And in this case, we can know that we can see that for the group case, the Hopf integral is just of this form, and for the dual algebra, the group algebra, the Hopf integral is just delta E. This is very crucial for the quantum dot model. Now we know that. Let me come back to this. Yeah. Now we know that we have the vertex operator here. We just need to construct to set an element into this vertex. This element is just Hopf integral, which means that we just take the co-multiplication. There is 4 edges, so we just take a co-multiplication. But here, the crucial thing is that we must choose the initial point, which is this initial site, and then we counterclockwise do the co-multiplication and put everything into each edge. Then we can construct such a operator, and it can be proved that this operator is a projector and it's a Hermitian. And for the face operator, it's very similar. We can just put a phi function over this face, and we take the co-multiplication over around this face, and for each edge we put a component into this each edge, and then we can show that these two operators satisfy this relation. This is called the straightening relation of the Hopf algebra, which means that locally on this site we have this 6 edges. This 6 edge is just the Hopf algebra tensor product 6 times, and all this Hilbert space, we know that it supports the representation of the quantum double of this Hopf algebra. So this is a lattice model of the Hopf algebraic quantum double model, and this is basically the Hamiltonian. Actually, the model is. If we construct the model, the first thing we need to consider is what is the excitation of this model. The excitation can be constructed from the Riemann operator. So we need to construct what is a Riemann operator. There is something that people that we do not observe before, is that there are actually 2 kinds of operators. We know that operator is just a ribbon is just like this. The ribbon has a direction. We know that this is a direction. This is also a direction. We'll find that the direct edge can be in the left-hand side or the right-hand side of these ribbons. There are actually 2 different ribbons. These 2 different ribbons, we construct the ribbon operators using the following way. We know that we have a quantum double of the Hopf algebra. We just take the dual of this Hopf algebra, and relation we need to use is that we use the co-multiplication of these Hopf algebras to construct the ribbon operators, which means that we define this recursively. We cut the ribbon into 2 parts, and we put the first element into this first ribbon, and the second component into this second part. So basically, if we define this recursively, we'll find that the basic building block is just these triangles. These triangles, there are totally there are 8 kind of triangles. Using these triangles and the Glooning relation we have given here, well, we can construct a ribbon operator, and we can show that this ribbon operator has the required property, which means that it's commute with all the local stabilizers, and only for the boundaries 2 sides there is some excitation over these ribbons. So this is the correct answer of the ribbon operator, and we can show that this ribbon operator satisfies this some other algebraic properties. And for the topological excitations, we know that for the finite group, we know that the topological excitation is classified by the conjugation class and the representation of the central group of this G. But for the Hopf algebra case, we can find a very similar structure, but it's more complicated. We know that for the group case, we must generalize this into into a mathematical form, which is just the CG tensor product MG as a representation, and this CG is also algebra in such a mathematical form. And the conclusion is just that we can have a very similar structure as the finite group case. So in this case, we can divide the electric charge and magnetic charge and the ionic excitations. And I'll skip this. And now let us consider the gapped boundary theory. Firstly, we can construct an algebraic theory of the gapped boundary, which means that we know that the input data of the quantum double model is just a Hopf algebra, and the topological excitation or the topological phase is just the rep of the quantum double. This is now we can consider what is the boundary theory or what is the boundary data of this Hopf double model. It turns out that the boundary is determined by the H co-module algebra, which means that the boundary input data can be chosen as a H commodity algebra. The boundary phase can be expressed in this form, which is AA by module. And now we can show that this is there is a dictionary between the quantum double model and the string-8 model. If we input the string-8 model with this C, then we know that the string-8 boundary is determined by the C module category. So this C module category is actually just the module, the A modules, the category of all A modules, and everything matches very well. So now the only thing is that how to construct the lattice model of this boundary of the boundary lattice. So now we need to consider the definition of this H commodity algebra. Let us just first solve the H commodity algebra, because the H module algebra is just the equivalent. These two models are equivalent. We can just transform one into another. So for the H commodity algebra, we know that there is an action. There is a left coaction from the A to the H tensor product A, and it satisfies two axioms. So this is not so crucial, but we want to say that our key observation is that the main data is that we need a special element of this H commodity algebra, which is called a symmetric separability idempotent. It satisfies these conditions, and we can construct a boundary. This bold edge is just a boundary edge, and the bulk is on the right-hand side. And for this boundary operator, we know that it's very similar like this. But the only way is that this action, we know that this boundary edge is we put a H commodity algebra here. So the action is very different. This action is just from the H dual to this A. So this action is induced by the H commodity algebra structure. And for the vertex site, we can do very similar things. But in this case, we must take the tensor product of these two A tensor product A, and we do this construction, and we can show that it matches well with the algebraic structure we have established. And now a crucial thing is that how to construct the local algebra that realizes this topological phase. We know that for the anion condensation, we have a boundary phase, we have a bulk phase. We need to construct algebra such that the boundary phase is just the module of these algebras, and we can show that there is such kind of algebra structure. This matches well with the algebraic theory we have constructed. So this is also a little bit complicated. Let me just skip this. And for the lattice model, we can show that if we just construct the boundary vertex and the boundary face in this way, we can show that it satisfies this straightening relation. This straightening relation means that we can, at the boundary site, we can construct a representation theory of this just local algebra we constructed into this boundary site. So at each boundary, it supports a representation of this algebra. This algebra is this representation. This module is equivalent to the AA bi module of the boundary phase. So it's still a boundary excitation. And a crucial thing is that if this is unique, actually this algebra is not unique. And we know that for the two phases, they are equivalent as a the boundary is one-dimensional phase, so it's just a unification category. And what is the relation between two different theories that realize? Okay, this can be related by the Morita theory. And finally, I want to say that this model can be solved using a tensor network approach, but this is a generalization of the tensor network. We must use the Hopf case. Well, for each lattice, we just cut it into this, and for each edge, we put an element. For each phase, we put a dual function from the dual algebra, and then we can construct a lattice model, tensor network representation that solve this model. Yeah. I think this, or I will skip this part. Okay. So basically, this is our construction of the Hopf lattice model. We have a complete theory of the Hopf lattice model, and this can also be generalized to the weak Hopf case. Yeah. Thank you.
Is there any question?
So I think you said the weak Hopf case is the most general. It can give rise to any fusion category and then any non-chiral topological order.
Yeah, I think for the weak Hopf algebra model, we can give all the non-chiral modular tensor category phase.
Okay.
Which for which the bulk phase is just a modular tensor category.
So how general is the Hopf case?
Hopf case is not that general. It can be
what's an example of let's say like the Drinfeld center of the Fibonacci fusion category? Like, is that realizable with Hopf?
This can be constructed using a reconstructed way. So we first have a unitary fusion category. Then we need to find a Hopf algebra that corresponds to this unitary fusion category. There is a mathematical way that we can do this. It's called the Crane-Tanaka reconstruction. We can reconstruct some kind of Hopf algebra first, and then we input it into a lattice Hopf lattice model. Then we can
if you start with certain fusion categories, you'll end up with a weak Hopf algebra as opposed to just a Hopf.
Weak Hopf algebra case, the tensor unit is not same simple. So there is some difference here. But in general, we know that the Hopf double model cannot give all the topological phase.
Okay.
Yeah, this is a conclusion. Yeah.
Okay. Thanks.
Any other question? So is the tensor network you obtained can be regarded as a MPO injective peps?
No, it's a generalization of the tensor network, because we know that for the tensor network there is some there's some contraction over this edges. But for this case, we just put some element of each edges, and for this circle there is some function. It's just another way of the contraction. So this is different.
And also the excitation you obtained has a quantum dimension, which is rational number?
Which is?
Rational number.
It's, yeah, it's true, yeah.
I see.
Yeah.
So time has come, so let's thank the speaker again. Okay, so the last speaker is Pasquale, and the title is Controlling Majorana Modes via Inhomogeneous Superconductivity in Topological Superconductors. Please start.
Thanks, and I thank you all for being still here on the last talk of the last session of the week. So I will focus very much on condensed matter physics. So I will talk about these Majorana modes, and which is well understood concept in condensed matter physics. And what I want to add is the concept of inhomogeneous superconductivity. So in order to, let's say, manipulate these Majorana modes with the aim to construct some topological quantum gate. So these are my collaborators, and so not very well. Okay. So Majorana modes are composite quasi-particles. You can think about like a superposition of a fermion and let's say a particle and an antiparticle, and they follow these fermionic anticommutation relations. And differently from ordinary fermions, they are their own antiparticles. So if you dagger these Majorana operators, you end up with the same operators. And they typically you can typically have it on as bound states edge modes of topologically protected phases, like symmetry protected phases, and they have zero energy, which basically means that their energy scales exponentially with the size of the system. And so what is interesting for quantum computation is that they have a non-abelian exchange statistics. So if you exchange these Majorana modes in space or in parameter space, it depends on the order of your operation. And so this can be used to build Clifford gates, and which basically gives you a platform for quantum computation, even though you don't have a quantum advantage, because if you have only the Clifford group, you basically can always simulate these quantum gates with a classical computer. So if you are interested, there's many reviews, but I recently I have a pedagogy review last year. So if you focus more on these aspects. So how you braid, how you exchange these Majorana modes. So you have a topological superconductor, like a one-dimensional superconductor with basically you have a superconductivity correlators, you have a broken time-radius asymmetry, and you want to control the domain walls, and maybe you want to arrange these one-dimensional wires in 3 junctions. And basically you can move these domain walls, and you exchange these 2 particles. So this is basically the main idea to build a quantum gate, a topological quantum gate with one-dimensional superconductors. But that's actually before even the one-dimensional idea is that you can have a 2-dimensional superconductor, and where Majorana modes, they localize at the vortices of the superconducting order. And in this case, conceptually, the braiding is simpler, because what you need is basically a way to manipulate, to move these vortices. And when you move these vortices, you exchange these 2 Majorana modes. And basically, in order to build this quantum gate, you just need to control the vortices. So the idea of our work is to combine basically these 2 ideas. So to have the flexibility of the 2-dimensional platform with, let's say, a one-dimensional system. So the idea is to embed a one-dimensional, let's say, stripe or quantum wire into a 2-dimensional system. And the way that we're doing this is to add this additional ingredient, is that this inhomogeneous superconductor. So just very quickly, so when you have in standard conventional superconductivity, you have a BCS state, which basically it's you have 2 fermions, 2 electrons on the Fermi surface with opposite momentum and opposite spin, and there's this Cooper instability which pairs these 2 electrons, forming what is called a Cooper pair, which has 0 momentum, because it's the momentum is given by the sum of this of the 2 electrons. But if you add a magnetic field, you may have a situation where your band structure and then also your Fermi surfaces is, let's say, it's asymmetric for by inversion, but you can still have a let's say a superconducting correlation, a superconducting order. But in this case, you need to pair electrons with opposite spin but with momentum which are like k and minus k plus q. So the total momentum of this Cooper pair is equal to q. And you can have these cases where basically, so these are called full de Ferrel Lacanian states. And you can have a superconducting order parameter which is basically has a constant magnitude and as a phase which depends on the space coordinate. And you can also have cases where basically you have Cooper pairs with q and minus q, and which if you add them, you end up with the order parameter which has let's say a modulated magnitude, because here then you end up with some cosine or sine depending on this momentum q and on the space coordinate. So then to implement this idea, we consider a concrete example. There's actually many ways to construct these full de Ferrel Lacanian states, but we focus on this system. So we have, for example, you have a topological insulator and proximatized by two superconductors. So you have the surface states of the topological insulator, which becomes proximatized. So, and this is the Hamiltonian. So this is basically your Dirac surfaces, Dirac cones. Then you have chemical potential. You have some symmetry breaking, time symmetry breaking magnetic field. And these are the couplings basically between the two surfaces. And then you have the superconducting pairing. So you have some ordinary singlet superconducting pairing, but you allow basically the superconducting pairing to depends on the spatial coordinate, and you can calculate this self-consistently in the usual BCS Bogoliubov-Dejean formalism. So if you just so you can write this Hamiltonian in the Bogoliubov-Dejean form, and where basically you introduce this additional Pauli matrices, this nu here, and you can calculate the topological invariant of this system. And this is the topological invariant is given by basically by the product of the Pfaffians of the Hamiltonians at the high symmetry points, time related symmetry points of the Brillouin zone. And this is so it depends on the coupling between the two surfaces, chemical potential, the magnitude of the superconducting order parameter by the magnetic field, and also depends on this phase phi, which is the phase of the superconducting parameter. So that means that basically changing either the magnitude of the superconducting the parameter or the phase, you can drive your system in and out of the topologically non-trivial phase. And this is it's valid for 2D, but also in 1D, which we will use later. So if you consider, if you put your system in a, let's say in a modulated inhomogeneous FFLO order state, where the order parameter has this general form, where Q is again the momentum of the Cooper pairs, you see that in general this depends on the so the magnitude and also the phase depends on the space. And what you have is that you can have stripes which are prepared. So let's say Q is on this direction. So you have different one-dimensional stripes which are alternatively non-trivial, trivial on the y, trivial and non-trivial. And here I calculate the local density of states at zero energy, and these are the peaks of the intensity of the local density of states corresponding to the Majorana modes. So at the end of this, at the edges of these stripes, I have Majorana modes localized, and this is the spectra. So this is the energy spectra. And typically, the order vector, this Q, the momentum of the Cooper pairs is equal to the is proportional to the magnetic field in plane, and also has the same direction. So if I obtain a superconducting order where Q is smaller, that means that the distance between the stripes is larger, and basically I can accommodate a single stripe in my finite system. So I have this system, this two-dimensional system, and where basically the inverse of Q is comparable with the linear size of the system. And now it's clear how I can braid these Majorana modes, because I can build, let's say, a domain wall here. I increase the chemical potential, or I change any of these parameters to drive the system locally out of the non-trivial phase. And so I get this domain wall here. So I split the stripes into two stripes. And now I mentioned that these stripes are perpendicular to the momentum Q of the Cooper pairs, which is parallel to the in-plane magnetic field. And basically, if I can imagine experimentally, I don't know if it's possible, but in principle, it's possible to rotate this magnetic field in plane on one side of the system. So then I can control one, let's say, one pair of Majorana modes independently by the other, and I can basically braid them. So these are all self-consistent calculations. So we just basically plug in some reasonable experimental numbers, and we calculate the superconducting order parameters self-consistently. And so so this you can exchange, let's say, 1 and 2 and 3 and 4. But to have the full quantum gate, I need to so the basic quantum gate is given by 4 Majorana modes, and I need to build all unitary exchanges, all braiding operators on these 4. And what I need is basically the exchange in 1 and 2, 3 and 4, and what I need extra is to exchange 2 and 3. So to exchange 2 and 3, I can so adiabatically split again these two stripes, as I showed before with the domain wall. And then if I can rotate the magnetic field on this side, on this part of the system, I can basically exchange these 2 and 3. And then what I need to do is again to merge this. So by the inverse operation, adiabatically I can merge this and this, and I obtain basically at the end of the process, I exchange these central Majorana modes. So you can describe all this system by an effective Hamiltonian. So you forget about all the superconducting or the parameter, and you say just, okay, the low energy physics is described by these Majorana operators. So on the left, on the right. So you have this coupling on the same side and the coupling W between left and right. And we can show that in some condition, if you tune, for example, W equal to W prime, and in the case that the number of the Majorana operators on one side is equal to this 3m plus 2, and there's actually other finely tuned cases, but for example, in this case, you have that there's exactly one Majorana so the Majorana modes hybridize, and you have a eigenspace, a low energy eigenspace, and there's one mode which has exactly 0 energy independently by the size of the system. So this is different from what I start with, where for example, if I have 2 Majorana modes, the energy is only exponentially small in the system size. But here I have exactly 0 energy, and in this case I can construct some supercharge, some supersymmetry operator, and which is described by this super algebra, and so the only caveat here is that this is a finely tuned point of the phase space. Another thing that you can do is that basically this can be thought in as an implementation of this such that Jia-Marra model. So basically, in this paper, there was this this proposal of engineer this model. So you have a so this is a strongly correlated model with random couplings. So basically, you have these Majorana wires, and you couple with a disordered quantum dot. So in this case, you need several quantum wire, but in this case, I just need one system. So I tune this, and I have these one-dimensional wires, which are also translation invariant. And so this can be a possible implementation of this SYK model. And yeah, so I leave with the conclusion, and that so basically we are trying to propose a system which is combines the flexibility of a two-dimensional platform with, let's say, the simplicity of one-dimensional quantum wires. And we show that this can have application for quantum computation, so to build a topological quantum gate, and has interesting property in the sense that you have some supersymmetry built in the system. And there's also it's maybe thought as a possible realization of the such the Jia-Marra model, which is interesting if you want to basically simulate the chaotic behavior of black holes on a condensed matter system. And that's all, and I thank you for your attention.
Any question? So what is the largest error of this Majorana modes in this model? Is it from overlap with neighboring Majorana, or more like quasi-particle poisoning stuff?
So what is the coupling?
The cause of the error. I mean, if you want to perform topological quantum computation by this, Majorana braiding, then what is most problematic?
Okay. So I think the most problematic aspect of these Majorana modes is that I would say that you cannot have a universal quantum computing only with braiding, because you need some extra operation which you can implement in principle, but they are not topologically protected. And another problem is that, of course, the size, the distance, the overlaps of these Majorana matters. So because if they are too close, basically the overlap basically lift the energy. So you have problem with the adiabaticity of.
So you had a graph of energy plot, and there is kind of slope in the middle that is basically finite size effect.
This one
before.
Yeah,
this one.
yeah. So because you have a 5, 10. So these are all 10. So this is the splitting, and yes, you have.
Ideally, they supposed to be in flat line.
But there's a gap, and in principle, if you stretch this let's say this low energy eigenspace becomes flatter, and but it's still protected by this gap, because the gap does not depend on the size of the system. And of course, there's also a problem with the numerics, because I don't want to have my system too large, because then it's more complicated. But in principle, if you make it large, this should shrink.
Any other question?
Yeah, maybe I have two questions. Maybe one is very related to the previous
Yeah.
question. So this dispersion is related to the hopping between the how to say Majorana sites or like in the vertical direction. So dispersion of the edge state, right?
So I think this is
It's
can be
dispersing, right?
can be
So yeah.
it can be understood by this effective Hamiltonian because if
Yeah,
you
it
plug
looks like
yeah.
the hopping between the Majorana sites, right?
And also if you take it this like if you consider several like several Majorana modes, you basically
But
have a chiral.
We can understand that can we understand that it is kind of the chiral hopping between the Majorana site?
Yeah, because basically then you end up with a one-dimensional chiral Majorana modes, and this is exactly the
Okay, got it,
dispersion.
got it. And another question is, you rotate the magnetic field, but in such case, there is how to say, you focus on the some kind of maybe low magnetic field, and you find out the single. Yeah, this one. But is there any problem like maybe if finite magnetic field there is a how to say neighboring edge modes even with a rotated case, but is there any issue like that? So like interference of that or something like that?
So
why does not appear such a neighboring edge modes?
You mean like
yeah. There should be some other modes.
Because
right?
basically what maybe I should have shown here. So I have here the chemical potential which is going here, and then there's a bump here. So this separates. So this is always trivial. So this part.
I
but
see.
of course there's also problem because you know you have to imagine how to connect these magnetic fields because you cannot have just a how to say discontinuity.
Yeah.
So this we didn't look so much because we assumed that there's some. So I basically smooth out the.
Is it impossible? Yeah. Okay. Yeah. I got it. And maybe
this is
like
maybe more technical.
Yeah. Like previous for example, like Jason Arici's proposal, they tune the chemical position like this, and they make domain wall. But in this case, you need to change the magnetic field itself, or I want to think about the for example, like making the gradient of the chemical potential or such directionality make the rotation or something.
So maybe a way to think about this in a how to say realistic way is that I have a gate with a chemical potential which separates basically in two systems, and then I have, let's say, a magnet here and magnet here, and which rotates. Or maybe
this is not so
or
maybe
you know I think you don't need something that is moving really. You can tune the magnetic field, but and of course if you I mean, this you have to calculate with the Maxwell equations,
right,
and
right,
there's some finite element methods.
Right.
This I think is more technical.
Yeah. Okay. I see. Thank you.
Thanks.
So this is the end of the session, the end of this workshop. Do you have any